All right. So yeah, I'll start. Please let me know if anything is unclear. Like I don't know how much background people have in dynamical systems theory. I've tried to explain at least some of the important things that I think are important to understand for the rest of the talk, but please let me know. Also to Amrit, I am not including your work, but maybe in the future when it's published, we can also include that in a future talk about dynamical models of fMRI.
Oh, he's
Um,
on.
yeah, he's on. These are mostly models from one specific lab. It's been like from 2017 until now. They've been developing these works. They've been published in a lot of different venues, ICML, NeurIPS, a lot of plus one plus computational biology. But I'll first start really quickly for people who are not as familiar, like what is a dynamical model? And for people who are familiar with deep learning, there has been a lot of interest in state space models again. Except in those types of state space models, they don't learn this A matrix here. They kind of have like a predetermined way to fill the A matrix. So it's not the same as like those types of state space models. In this case, when I'm talking about dynamical models and fitting dynamical models, we are learning the A matrix. So it's like it's different from like state space models that you now oftentimes see in the deep learning literature because they have a like a predefined A matrix.
Do you want to make it full screen later?
Yeah, I can't for some reason. Then it like doesn't, I think. See, now it's gone.
Oh,
I can maybe do my whole screen. Let me,
okay. But then, no,
no, let me, I'll just do my whole screen and then I can make it full screen.
but there is another one. There is.
Here.
Perfect.
All right. So it's the way it works, the way is everybody familiar with this type of like visual or notation? This just means like essentially time step t plus one is dependent on the A matrix times x plus b times some input vector. So like um, you can think like let's say we remove the input vector, like the b and the input vector matrix. This is like a system of equations where let's say it's 3D, like x is a 3D vector. It'll move through space based on the values in the A matrix. If I go further in here, this is an example, for example, of like um, a dynamical system. So this would be like three Z1, Z2, and Z3. And then over time, it'll kind of like form this shape. Like this is kind of its shape. And uh, in a linear case, you can visualize it as this. It is like a matrix um, A that kind of determines how each vector um, affects each other vector's trajectory. So like if this is an identity matrix, all ones on the diagonal, it's just going to be a straight line because each vector is going to keep going straight forward because it's going to be xt plus 1 is going to be xt, and then xt, yeah, xt plus 1 is going to be the exact same as xt. Anyway, sorry, I'm not trying to like confuse people here, but just so people understand. Why is this interesting? Actually, a lot of things that we do in fMRI are in some sense like related um, to dynamical models. For example, a functional network connectivity map. You can think of it as this like system matrix A, especially static functional connectivity. I mean, it's not the same, but like
Better than
it is much better. Yeah, it's much
simulation.
better than. But like in some sense, I guess I mean static functional connectivity map is in some sense trying to get at this A matrix
But it's
with the
easy. It's correlation.
extremely oversimplified assumptions. Yeah, I agree. I agree. But
A
in some
is much better. A is causal. A is
yeah,
actually
A
like
is the actual dynamical system. SFNC is a very simplified version of trying to get to this like A matrix. But you can think of it as like a derivative of it in some sense, right? Like um, um, it's just more my point is more that we have been trying to get at dynamical systems through kind of different ways before. Um, these papers are trying to get at them kind of directly. So SFNC would be a very indirect way of trying to get at this A matrix. What? I meant like static FNC, as in like over the whole time series, because we also sometimes do like windowed. And obviously, in this case, you're assuming A to be the same for all time steps. So we can't like that would not be the same as like the yeah. So what are some other approaches? Dynamic causal modeling is an approach that was developed by Carl Friston in the early 2000s that people have worked on. Criticality in neuroscience is a big thing where we look at, for example, when a state collapses to another, especially if you,
Just a comment for the dynamical modeling. He's using exactly this equation.
yeah, exactly. Yeah,
But then hemodynamic,
exactly. Yeah. But he doesn't like fit it, I think. It's like a little
no,
different.
It fits the eight.
Yeah, but I think in a
No.
different, yeah.
But you can test.
Yeah, exactly. That's what he
Two
does. Yeah.
models.
Exactly. But these are early works essentially trying to get at this. Like criticality, neuroscience is big. We both use it in whole brain, but oftentimes you see these things in like neuron models because for neurons, we actually know the dynamical system model. Like the Hodgkin-Huxley model is a way to describe the firing rate of a neuron. That's a model that we can then look at and see when it's critical, which means that, you know, a state collapses to another. And then we can look at stability of brain dynamics, which I'll show you in a slide, in the next slide, and then also brain attractors. So what are attractors? This is just to get people like a kind of a visual of what I'm talking about. I mean, there's many different ways, but like this is one way of looking at the brain or like at dynamical systems. So for example, this is an example of what we call point attractors. Essentially, if you think of this as an energy landscape, like a ball that is rolling around in this landscape, right? If I put the ball here, it'll end up in this point attractor. And if I put the ball here, it'll end up in this point attractor. If you just think of it as like rolling down the hill. Um, that's what we call point attractors. Then there's like ring attractors. So in this case, if I let the ball roll here, it'll end up in any kind of like point around this, like depending on where I like put the ball, it'll end up in this ring essentially that is here in the middle. So those are all the points that like the ball can end up in. That's what we call it a ring because it actually forms like a ring in the space that we're thinking about. There's a few other ones. This is another way to look at it. Like point attractors kind of go to a point. Ring attractors, they go to this like specific like circle. Maybe is good to think of in the space. There's torus attractors, which are 3D versions of ring attractors essentially, and then you have sheet attractors, which are 2D versions of point attractors because now it's a whole sheet.
Cycles are interesting. Can you talk about the difference or what's the difference between a ring attractor and a cycle?
Yeah, a ring attractor is one where the point ends up in a like in the ring and then it stays exactly in the same spot. And a limit cycle means that it goes around the ring constantly. So you can see here this limit cycle. It means that it's essentially stable, right? Because it doesn't get out of the ring. I think actually Alex sent like a paper about this kind of recently, but like it's still stable because it stays in the ring, but it's not static. So it doesn't like it'll stay in the same space.
Only game of life, if you've ever seen it, whether breathers are the example, something that moves around the same, like it's an animation, it's a breather. Something is moving and cycling.
Right. So it's kind of interesting because then in some sense, like you are stable, you're in a like a specific attractor, but you're still moving around. Um, exactly. It's an equilibrium. Yeah, exactly. So stability, the way we can actually measure stability. So I just showed you guys like point attractors, for example. These are all point attractors. And you can see that like it kind of pulls towards the point. There's different ways that you can go towards a point. So there's ways that you can just go directly to a point. That is when the A matrix that I just talked about has only real eigenvalues that are smaller than zero. It'll go straight in a line towards that point. Those systems are considered like really stable because anything you do, it'll always end up in that place. Like if you think of like a really stable system is, for example, e to the power minus t, it'll always go to zero, right? Like when I take t to infinity, it'll go to zero very quickly. That would be a very stable attractor. There's also different ways, like you can also have it be kind of like a circular um, eigen attractor. So like in that case, it'll kind of like go in a circle towards the point. That's when you have imaginary values. The reason for that is because imaginary values are essentially sines and cosines. And so you get this kind of like this shape that I show here below. Then you have like Lyapunov stable, which are like things such this would be, for example, one of those limit cycles is like it stays the same constantly, but it doesn't go to like a specific point. And then you have unstable systems that kind of move away from the point. In fact, like these are all examples of unstable systems where the real part of the eigenvalues are larger than zero. So to go to like the exact work that they've been working on, they work on PLRNNs. And so honestly, the only difference for people who are familiar with deep learning is that they use ReLU activations instead of any other activations in their dynamical system model. So this is what it looks like. I mean, here you can see that A matrix that I talked about. They add a W matrix times the ReLU activation of the hidden states. And then they have this input matrix that I also showed times the input and then some noise. So this would be like a pretty normal way also of thinking about a normal RNN, except that in this case, the hidden states have a ReLU activation on it. The reason they specifically use RNNs also is because of the universal approximation theory. Like they essentially say that there's been work before this that says you can approximate technically any dynamical system with this equation. Now, whether you get that out of it when you fit it is obviously a big different question. I mean,
about the diminishing on exploding gradients.
yeah, that's actually interesting. I mean, I don't have it in this paper, in this work, but they have a lot of papers recently that came out about generalized teacher forcing, which is actually a way to reduce exploding gradients for chaotic systems. It is technically included in one of the papers just that I'm talking about, but I'm not talking about exactly how that works because I think it's like, otherwise it becomes too much. But yeah, this is their model. So the only difference from the one that I showed you essentially here is that now there's a ReLU activation on the state vector. That's how you can think of it. Um, so, all right. Why is it interesting to use ReLU specifically? So like they give it a new name, right? Like piecewise linear RNNs. Why is it interesting specifically to be piecewise linear? The reason is that you can actually get uh, analytically solve, which is not true for normal RNNs, and analytically solve all the fixed points and they're kind of like the eigenvalues and like the features around those fixed points. And that's interesting because in dynamical systems theory, we use those things in physical systems to understand the system. So when you have a physical system, you oftentimes look at things like what are the eigenvalues? How many fixed points does it have? Does it have a limit cycle or not? Those are ways to kind of like understand the system from a more abstract level. And the reason that they can do this is because it's piecewise linear. There's going to be some units that are going to be zero, right? Because of the ReLU activation. That's what they mean by the ZM is smaller than theta M. And some of them are just going to be completely linear because they're above zero because of the ReLU activation. Only the ones that are below zero are going to be zero, and everything above zero is going to act like a linear system. So that's what's really interesting is that you can actually analytically um, solve these fixed points. And the reason why that's interesting too is because a lot of people have looked at ways to finding fixed points from nonlinear systems, and it's really, really, really hard, especially to do it in like in a way that always gets to the same solution. So in my own previous work, I've done that with like nonlinear systems. Really hard. You need to make a lot of assumptions. You don't really know if it's going to be like correct most of the time. Um, So that's what's really positive about this work. And that's why they've been working a lot with these piecewise linear models. And so then the decoder model. So what I've been talking about now is all these like latent dynamics essentially that underlie the brain. The way that they just map it to actual brain activity is through a linear matrix. So it's not really that complex. Um, Honestly, most of the time in the papers that I'm going to be talking about later, their latent dimensionality is going to be the same as the fMRI or like brain dimensionality. So, but I just wanted to show this to give you like a full idea of what the model looks like. All right, is everything clear so far? I mean, at least from like a
Just questions. The
yeah.
number three is practically the that you have a five function. Okay.
Yeah, this is the ReLU.
It's a bar vector regressive model.
Exactly. Yeah. So the only difference here is that they have a ReLU activation on it. And the B is just a linear matrix.
Mhm.
You can also just like remove essentially like the eta and stuff. I mean, they add them because they're technically assumptions, but because it's like Gaussian, you know, essentially, essentially doesn't really matter.
Well, no, you have to have the random perturbation for the system to evolve.
No, that's true. That's true. But I mean, more like when you're fitting it, obviously you're, it's nice that it's Gaussian. All right. So what's the difference then when we apply this to an fMRI data framework? So at least their claim, for example, is that it's really important to take into account the HRF, the hemodynamic response function that we have for fMRI data, because if we want to find a dynamical model that models the neural activity, we should take the HRF into account. Um, that's a big assumption, obviously, because we don't really know what the HRF looks like or how it changes across the brain. It's sometimes different for different subjects. It's different sometimes across different time steps. It's sometimes different across different voxels. But anyways, this is the new decoder model essentially. So when we go back, you can see here we have xt equals b times the ReLU of the latent variables. The main difference here is that they essentially say we're going to add an HRF here that is convoluted with the latent variables.
Doesn't complicate things a lot, this convolution operation. I mean, it's linear, but at the same time.
So yeah, I mean, I'm not going to go into too much how they exactly do it, but they essentially just do a Wiener deconvolution before they fit the model. It's, yeah, I think there's better ways. A Wiener deconvolution, it's like the optimal Gaussian deconvolution.
So you
Yeah.
like you have this star there, asterisk. So it's convolution with an HRF equals response.
Yeah,
That smears everything.
exactly.
You can deconvolve if you know how HRF is.
Yeah, that's what they do. So they say essentially we know beforehand what the HRF is, and then we can remove it again from the signal. Um, this is an example, for example, of what like a Lorentz system looks like when we do the normal version and the one that is convolved with the HRF. So like Sergey said, it smears it a lot kind of across. It becomes kind of slow and things like that. Anyways, this is like, it's kind of interesting because it's also very similar to a GLM model, honestly, from an fMRI perspective. I'm sure you can also see, Sergey, here, the nuisance regressors. You have the HRF, and then you have this big B matrix that we normally fit to task fMRI data. All right, so that's what they're doing. And to measure, so they're going to start looking at simulated data first. This is the Lorentz system. It's a very common system for people to look at because it's chaotic, so it's hard to predict, and it's low dimensional, so it's easy to do simulations for and also to do experiments on. But I think first what's interesting is that they say, well, if we want to measure the similarity to the underlying system, if it is a chaotic system, um, this may not be clear for a lot of people, but like, I don't know if people have heard about the butterfly effect. If you have a really small change in initial conditions, and this can literally be like epsilon, like your computer epsilon, essentially, over time, that will lead to differences in, like, for example, if I give Pavel the initial condition 0, 0, 0, and then I have 0, 0, 1e to the power minus 32, at time step 100, our differences are going to be exponentially large. Like they can be like on the order of like 10 to the power 4 or something. That's like how crazy it is with chaotic dynamical systems, because even really, really tiny changes in the initial condition can completely change the state of the system for me or for Pavel at a certain time step. So the first thing that they say, I mean, this is, yeah, exactly. both that and also how good you can like measure performance on predicting these dynamical systems. So what they say essentially is like, because we know this about chaotic dynamical systems, instead of trying to to look at the mean squared error between predicted and true states for the dynamical system. They actually look at the KL divergence between like a freely simulated model of the true dynamics and the actual underlying system. So when you fit your model to the data, right, you get like a model that you can now simulate, a generative model that you can give an initial condition, and then you can look at how your fitted model evolves, and you can look at how the true model evolves for that initial condition. What they say essentially is instead of looking at the exact predictions, which is hard to do, also partially like William pointed out, we're going to look at the geometrical similarity. So like, does the shape of the underlying system, if we simulated for, let's say, 100,000 time steps, does it look similar to the geometrical shape of the of the true system? And here they show some examples of like this would be a good fit under their similarity metric, which is based on the KL divergence, and this would be a bad fit uh, of the system. So you can see that, like, let's say this model here, the orange line is their fitted model. You can actually have a really, really large mean squared error between the predicted and the true system because it's a chaotic dynamical system. But in some sense, when you look at these two systems, like the black and the orange, they look almost identical when you place them on top of each other over like 100,000 steps. So in some sense, we want these two to be similar because they, yeah, go ahead.
Stupid question. Can't you do some kind of Monte Carlo marginalization across the initial states, initial conditions? So you start with different initial conditions, even slightly different, and see the average behavior, even more average than just that, because this is with just one initial condition. Right?
Well, in some sense, you're doing something similar to what they're doing, right? Because a million initial conditions, like if you think of it as one cycle, right? In some sense, when you do one initial condition and then just let it go for 100,000 steps, you're doing maybe like whatever, like 1,000 different of these cycles. So in some sense, we're doing a lot of different initial conditions. And by taking the average, you're taking some sort of like statistical a measure of this. So in some sense, it's kind of similar. I mean, it's not exactly the same, but I think in terms of ideology, I think it's kind of similar.
Yeah, kind of on that doesn't follow.
Right, exactly. Right. So in this case, what you're just doing is saying, how often is a point in a specific bin versus in the true system and this system? Because that's how you calculate the KL divergence for this type of data.
Oh, but sorry.
Go ahead.
This is about the most what they treat this 3D space as where the distribution is
Exactly.
defined.
Exactly. Yeah, that's exactly how it works. Yeah.
Okay.
So that's why it's kind of like a geometrical similarity, right? If the distributions occupy the same kind of 3D part of the space, we would say that those two models are similar. So they fit their model with this HRF system, which is called the conv SSM, on these Lorentz systems. And for the Lorentz system, we actually know what the eigenvalues are going to be, like what they should be. The true lambda max, because it's a chaotic system, it's going to be 1. And they show essentially, like, compared to one of their old models, they show essentially like how well they're able to fit these models. And this is a distribution of what maximum eigenvalues they get for the models that they're fitting to the data. So, you know, you could essentially what they're trying to show is that conv SSM is doing much better than conv SSM without generalized teacher forcing. That's why I said like it's sort of comes in this this slide. It's just about how you train the model. I don't think it's like super necessary to go deep into why or how you're doing this, but just think about, like, you can see that clearly their new model is doing much better in fitting the eigenvalues. And I think what's really important about this slide is that you got to think about the fact that we can actually now look at the fitted model's eigenvalues. That is really, really unique in terms of like maybe also for fMRI data in the future, right? Like if we can really look at, like, this tells us something about the stability of the system. And let's say your hypothesis is for schizophrenia, the fitted dynamical model is going to have is going to be less stable than for controls, let's say, right? These are things that we can now actually look at with an analytical model instead of having to do it numerically. They also look at simulated fMRI data. I added this for people who are interested, but like they're just doing like whatever spiking neural network, and then they're doing the balloon Windkesser model, kind of similar to the dynamic causal model. I don't think this is interesting for people to really focus on too much, but just so you know what it is. Um, and they show again, this is their measure for how good it's working. So let's first look at plot D. On the x-axis, we have the KL divergence here. So lower is better. And for both the observed data and the latent data, because we both know both for the simulated data. So I think what's interesting here is that for the observed data, actually their standard model does as well, it seems like, as the model with the HRF. But when we look at the latent time series, so these would be like the actual neural activity, the conv SSM does a little bit better. The reason why these are distributions is because they fit this model with different random like they're neural networks, right? So you have to initialize them with some matrix, like a random matrix. And they do this like 10,000 or like 1,000 times, let's say. And then they look at the distribution of how well these models are working. So in that sense, I think that's like good practice for like in terms of like how often do you get the correct correct system fitted.
You know why standard model is so good?
I I mean, if I had to review this paper, I would have definitely also said like this is a big question about like, yeah, it's just, I mean, if you're fitting the observed model, in some sense, the HRF, right, is not really that complex. I mean, especially the one that they're using. So I guess you can just fit that too. I mean, it doesn't really, you can fit both, right? I had this discussion with Vince actually 2 days ago where we were like, I mean, we don't know how important the HRF is. Like maybe that's something that we actually want to know about when we're like looking at psychiatric disorders. So in some sense, doing a
But they are
deconvolution.
different.
Exactly.
Demonstrated.
Exactly. So in some sense, I mean, it makes sense that you can get the observed the same. I think that makes a lot of sense. But one thing that is important here is that like the neural activity that they simulated and then did the balloon Windkesser model, which I guess is currently like the best way of simulating neural activity to fMRI signal. It does a little bit better than the normal model because that's the difference between latent and observed. Observed is the actual fMRI model, fMRI activity. Latent in this case is the neural activity.
It will be more spiky, right?
Yeah, which I were oftentimes, I guess, interested in, at least most people who study fMRI data. Um,
Yeah, the latent, okay, got it. Latent is that X that you put through, so you have.
exactly.
Yeah, so you have a way to go from X to Z and then blah, 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 but you want to recover X.
Right. Yeah. In this case, they call it Z, but yes, exactly. The thing is that this would be the observed data, X, that's the input model that we have, fMRI, bolt signal. And then Z is the latent time series that we obtain fitting this model.
To the original figure.
Yeah, I understand. I understand. Yeah. And then in E and F, what is the y-axis normalized counts? Yeah, so because they do multiple, they fit like 1,000 different models with different they like I said before, the neural network needs to be fitted with you need to initialize the neural network somehow. So they initialize it 1,000 times, they fit 1,000 of those models to the same data, and then they look at how well it performs across those 1,000 trials, let's say. Because, if you're fitting it to real data, it depends, the fit depends a little bit on the initialization condition for your neural network to train. So it's not the initial condition of the dynamical system, but it's the initial weight matrices that you're starting with when you're training your neural network model. And they're just showing here that like most of the time, this new model they have does better than old models, essentially, which I think is good because you'll see this in the last part, but they actually find that on real data, they have a huge underspecification problem where it's like really, really tough to like get the same metrics for a subject. So if they fit a model 1,000 times, they get different metrics for the same person, which that's a big issue, obviously, if you want to use it, let's say in a real setting, like a real clinical setting. Um, I hope that's clear. This is E is going to be looking at a long versus short test set, and then the values here, both on the X and the Y axis, are going to be again this scale divergence. The reason that they do this is because for fMRI data to test whether our model is good, we're only going to have access to very short time series, right? Like when I'm talking about this Lorentz system, it's 100,000 time steps. We don't have 100,000 time steps for any individual subject for fMRI data, especially not like consecutively in the scanner. That's like that would be, you would have to force someone to be in the scanner for like 3 days or something, or maybe even more.
Somebody has done it.
What?
That's somebody in Germany.
I would not be surprised. Yeah.
Look, that's look is less than funky. The Forrest Gump experiment. So
They're really long.
There's some people playing with it. Probably will try that.
Well, actually, there is I think Russ Poldrack did a study where he did it for like every day for a year. He scanned himself,
Oh, yeah.
but that is not consecutively.
Nothing-
Yeah. And then the last one, F, is for the observed in the latent time series, again, the KL divergence. And they just also showed the correlation between the KL divergence for a short segment and a long segment. The reason why they're doing that is to show, okay, well, even if we test it on a short segment, the KL divergence that we get for the short segment is going to be similar to the one on the long segment. So in some sense, we can already infer how good our fit is based on a short segment, right? And this is simulated data, so you can do that here because you have both the long and the short. This is just for their next step, which is going to do it on real fMRI data. So yeah, these are some examples when they do a fit on real fMRI data. And I think this goes against some people's maybe like what they would do, but they fit one model, they fit like their whole neural network model on one subject. So like we're really talking about like 300 time steps. They're fitting the whole neural network model on that subject because they're trying to get dynamical systems features per subject. So they don't do it across subjects. They don't like normally if we train neural network models, right, we're training it on a whole data set of subjects. Like we're not doing it per subject.
We want to generalize to
The new subjects. Yeah, exactly. But here what they're saying is we're going to just fit it on one subject at a time. And this is an example of one of those subjects. Again, they're just kind of showing their KL divergence metric to show like what are good fits and what are bad fits. This would be a really good geometric fit. And it does look pretty similar in some sense to the actual fMRI signal.
of the envelope.
Right, exactly. So again, also, this is why they're doing this geometric stuff, because you can see that the actual signal doesn't look very similar, right?
This does look like a read state.
No, it does. Yeah, I agree. Yeah. It doesn't look the same on like a time to time, on like a exact time. You can see that they diverge, right? They're not exactly the same time series. But in some sense, if I go back again to this, like what they geometrically look like, this first one here in D is the same as this one here in B. So I'll just let you take a photo and then. So in some sense, yeah. So in some sense, we can see here, like if we let it run for a pretty long time, the envelopes and kind of the shape and stuff looks pretty similar. But when we look at from a time to time point, like measure, like if you measure the mean squared error, it would be pretty high here. But in some sense, the issue here is that the mean squared error for this one could have been worse than for this one. Whereas if you just think about like geometrically, this one is way worse because it doesn't at all look like natural fMRI signal. And this one does look way more like natural fMRI signal. So I think one thing that I think is important to take away here is that I think they developed, this is not specifically in this paper, but like they developed this like geometric similarity measure, which I think is pretty interesting for measuring similarities between fitted dynamical models and fMRI data.
In the sense, scale divergence is not such a bad metric because it measures distribution, not the exact shape. And
Exactly.
C distributions are very different.
Exactly. But whereas the MSC could have been better than for B, which is kind of interesting. I think also I've seen this a lot in neural data because in neural data where they like record from a monkey, for example, inside the head, what they want to look at is like the neural activity will change over time, right? Because like the things that are implanted in the head will move, the neurons will adapt, and like things will change in terms of like what the exact data looks like. They also just look at the KL they oftentimes also look at the KL divergence because it's not like you would expect exactly like a monkey doing the same thing to have exactly the same data the next day, right? Even though they're doing exactly the same task, but you want at least some sort of similarity in the distribution. And these are just like the KL divergences for the inferred models um, across different random seeds. And they just show like what would it have looked like if it was a fixed point and what it does it look like if it was a white noise. So in some sense, they're just showing like clearly, they're fitting something interesting because it's doing way better than white noise and a fixed point. That's the point of those lines in the A figure here. All right, so now we're getting kind of to more of the interesting stuff, and I think there's a lot to do because clearly a lot of stuff is like not working super well yet, because it's just so hard to find the same measures um, for the same subject. But I think the most interesting figure here from this whole paper, in my opinion, is this one, F. So what they're doing here is they're showing the maximum eigenvalue of their dynamical system, and they're showing a distribution for each of these subjects. And although obviously there's overlap between the distributions, I think the one thing that I would say is an interesting takeaway is that they are definitely different between different subjects. So you can see, for example, that this subject has much higher distribution of kind of higher eigenvalues. It's not very high, it's 0.05. And like this one, for example, has a distribution that is focused more near zero. And I think that's interesting because it kind of shows that like there's differences in these dynamical systems between subjects. They have another figure that I didn't include here, but they kind of recapitulate that point there. That once we fit these models, we can actually find differences in their features, essentially, dynamical system features. So, it's not great yet. This is going to be another paper that just came out in August. They're trying to do psychiatric disorder identification with dynamic features. I just showed you here what the features are. I mean, it doesn't really matter too much, but like, they do things like total number of fixed points, the number of unstable fixed points, the average of absolute imaginary eigenvalues, the average of the maximum eigenvalues, number of stable cycles, the average, let's see, the average variance of the latent states over time, et cetera. So it's a bunch of different dynamical system features that you could normally not get from fMRI data very easily. And they try to use it to predict psychiatric diagnosis. And then the idea is that once we know which features are important, that'll tell us something about like fMRI and psychiatric disorder. So it's kind of to be very interpretable because let's say we know that like people with schizophrenia have more unstable dynamical models, then that tells us something about schizophrenia potentially. Anyways, the first issue arises very quickly in the paper, which is essentially that like it is incredibly hard to get repeatable features. So what they're doing here, B, is the Euclidean distance between features extracted from different models. So they're doing again the same thing that Amrit also just asked about. They do 100 or they do like 1,000 models per subject. And then they look at the distribution of distances between each of these models and the features. And you can see already that like the Euclidean distance goes up to like 20, which is very high in this feature space. And it's a big issue because like, what is to say that one model is better than the other? Like, we don't really know which of these models is like the best one because we randomly initialize them because they're neural networks. So that's a huge issue. Um, they go on further in the paper. I mean, this is not super interesting anymore, but like, I think that just to show that like they do some sort of like graph clustering, and then they say that that really helps with like predicting schizophrenia versus controls. Um, um, it's pretty interesting, but I think just it doesn't really relate as much anymore to dynamical systems model. But just so you know, it kind of works at least to some extent. Um, that's essentially like the final thing that I wanted to show. And then similarly to what I said on Slack, if you want to collaborate or talk about this more, reach out to me. So I've been reading and working on this. I've been working on this for some time, but reading this specific work the last couple of weeks.
Very interesting. Thank you
Cool.
for volunteering and presenting and giving the tutorial in the beginning with all of that. That's useful. Anyone, any questions in chat?
You mentioned some way to measure geometric similarity.
What do you say?
You mentioned some way to measure geometric similarity. What was this paper?
I will take a look at what the exact paper is where they introduced this, but they use this in all of their papers essentially now. I think it's smart. I think they use a couple of other metrics. So they also look at, is the frequency spectrum the same? But this is that like geometric similarity. Essentially, they're looking at the distribution of points and saying, are freely generating systems. So they don't use any inputs. They just say like, here's an initial condition, just simulate for 100,000 time steps or even more. Is it similar to when we simulate freely our underlying true system? And then they look at the distribution of points and stuff like that. Right. Yeah, exactly. Because once you essentially make these points into a distribution from the true and the generated system, you can then look at their Tail divergence and you can compare them. Do they look at the coefficients, the A matrix, and how it compares to known brain structures, FC or SC? No, they don't. To your question, Almrit, they don't. At least not in a paper that I've seen. I mean, they may do that in another paper. They have like 12 of these papers. But like the ones that I'm showing you here today don't do that.
Students from professionals, they minimum publish millions 12 papers. It's
Right.
not like you wait until everything is done.
Right.
Have something you publish it, yes.
Yeah, it's also kind of funny because like he built his lab, I think mostly now at least around this. Like he published his paper in 2017, Dr. Durstowitz, and then he has all these people who are working on different applications of it essentially. Like one part of the lab is really focusing on improving the original model, the PLRNN model. And then there's also a section of the lab that is focusing on applying this for fMRI and psychiatric disorders. So Dr. Georgia Kopa is someone who's really focusing on like the psychiatric disorder aspect of this. And then there's a few other people who are more focusing on the math and the development of this. So I think that's also kind of cool. I mean, it's not the only thing the lab does, but it's definitely a big part of the lab.
Any other questions, discussions, points, and online as well?
Some people do like clustering on like the DFNC here,
Mhm.
and when they find those states, which is kind of like different versions of the DFNC.
Yeah.
But this is like more of some kind of like what is the difference between those kind of states that people find in clustering and then this kind of states?
Yeah, so I think I think that's a good question. It also goes back to like how similar is FNC to like this dynamical system A matrix essentially. I think one big difference already is that in this case, you are assuming that the A matrix is the same across time. So I think a big thing with DFNC is that we're essentially assuming it's non-stationary, right? So it changes. Like if we did the same thing with this model.
The A matrix can be the same structure.
Yeah, that's true. That's true. Yeah.
Just change a little coefficient values.
Yeah.
And it will change everything. So it could be the same,
Right.
the same kind of structural zeros.
Right.
Zeros are the same.
I think the most important thing to think about is that anything that we observe with FNC and DFNC comes from, in its essence, this A matrix. This A matrix is like a summary of all of it, essentially. If that's like some way to think about it, because the whole dynamical system that we are trying to measure, let's say with FNC or DFNC, is defined by, if you assume there's no inputs, this A matrix, because it kind of like tells you exactly how it evolves. An FNC would be similar, like the DFNC would be similar. We would probably find these two, in this case with this Lorentz model, we would probably find these two states, right? This circle and this circle probably, because they have different correlation structures, right? Because of like in this case, we would get a 3x3 matrix for the SFNC of the Lorentz system. But in some sense, what we're trying to get at is this system, and the system is defined by A. FNC and DFNC is some sort of measurement that we're trying to kind of look at more from the outside at the system and not really.
Quick example
Yeah.
in a second, but I want to stop the recording.